Section 1.3 Multiplication and Division of Whole Numbers. In this video, we will learn how to multiply and/or divide whole numbers with the commutative property of addition, the multiplicative identity property, the associative property of multiplication, larger whole numbers, order of operations, and applications of counting rectangular arrays and area. Section 1.3 Multiplication and Division of Whole Numbers. We begin this section by discussing multiplication of whole numbers. The first order of business is to introduce the various symbols used to indicate multiplication of two whole numbers. So in the following table we have the mathematical symbols that indicate multiplication: the times symbol, the dot, and parentheses. Products and factors. In the expression 3 times 4, the whole numbers 3 and 4 are called the factors, and 3 times 4 is called the product. The key to understanding multiplication is held in the following statement: multiplication is equivalent to repeated addition. Suppose, for example, that we would like to evaluate the product 3 times 4. Because multiplication is equivalent to repeated addition, 3 times 4 is equivalent to adding 3 fours. That is, 3 times 4 equals 4 plus 4 plus 4. Thus, 3 times 4 equals 12. You can visualize the product 3 times 4 as a sum of 3 fours on a number line, as shown in Figure 1.6. Like addition, the order of the factors does not matter. It is also true that 4 times 3 equals 3 plus 3 plus 3 plus 3. Thus, 4 times 3 equals 12. Consider the visualization of 4 times 3 in Figure 1.7. The evidence in Figure 1.6 and Figure 1.7 show us that multiplication is commutative. That is, 3 times 4 equals 4 times 3. Commutative property of multiplication. If a and b are any whole numbers, then a times b equals b times a. The multiplicative identity. In Figure 1.8a, note that 5 ones equals 5. That is, 5 times 1 equals 5. On the other hand, in Figure 1.8b, we see that 1 5 equals 5. That is, 1 times 5 equals 5. Because multiplying a whole number by 1 equals that identical number, the whole number 1 is called the multiplicative identity. The multiplicative identity property. If a is any whole number, then a times 1 equals a, and 1 times a equals a. Multiplication by 0. Because 3 times 4 equals 4 plus 4 plus 4, we can say that the product 3 times 4 represents 3 sets of 4, as depicted in Figure 1.9, where 3 groups of 4 boxes are each enveloped in an oval. Therefore, 0 times 4 would mean 0 sets of 4. Of course, 0 sets of 4 is 0. Multiplication by 0. If a represents any whole number, then a times 0 equals 0, and 0 times a equals 0. The associative property of multiplication. Like addition, multiplication of whole numbers is associative. Indeed, grouping 3 and 4, we get 3 times 4 is 12, and 2 times 12 equals 24. And if we group 2 and 3 instead, we get 2 times 3 is 6, and 6 times 4 is 24 also. Therefore, multiplication is associative. And the general property is, if a and b and c are any whole numbers, then whether we group the product of b and c or the product of a and b, the two expressions are equal. Multiplying larger whole numbers. Example 1. Simplify 35 times 127. Solution. Align the numbers vertically. The order of multiplication does not matter, but we'll put the larger of the two numbers on top of the smaller number. The first step is to multiply 5 times 127. Again, we proceed from right to left, so 5 times 7 is 35. We write the 5, then carry the 3 to the tens column. Next, 5 times 2 is 10. Add the carry digit 3 to get 13. Write the 3 and carry the 1 to the hundreds column. Finally, 5 times 1 is 5. Add the carry digit to get 6. The next step is to multiply 3 times 127. However, because 3 is in the tens place, its value is 30. So we actually multiply 30 times 126. This is the same as multiplying 127 by 3 and placing a 0 at the end of the result. After adding the 0, 3 times 7 is 21. We write the 1 and carry the 2 above the 2 in the tens column. Then 3 times 2 is 6. Add the carry digit 2 to get 8. Finally, 3 times 1 is 1. All that is left to do is to add the results. Thus, 35 times 127 equals 4,445. Alternate format. It does not hurt to omit the trailing 0 in the second step of the multiplication. Where we multiply 3 times 127, the result would look like this. In this format, the 0 is understood, so it is not necessary to have it physically present. The idea is that with each multiplication by a new digit, we indent the product one space from the right. Division of whole numbers. We now turn to the topic of division of whole numbers. We first introduce the various symbols used to indicate division of whole numbers. So in the following table, we have the following mathematical symbols that indicate division: the division symbol, a fraction bar, and the division bar. Note that each of the following say the same thing, that is, 12 divided by 4 is 3. Quotients, dividends, and divisors. In the statement, the whole number 12 is called the dividend, the whole number 4 is called the divisor, and the whole number 3 is called the quotient. Note that this division bar notation is equivalent to the following two examples. The expression a over b means a divided by b, but this construct is also called a fraction. The expression a divided by b is called a fraction. The number a on top is called the numerator of the fraction. The number b on the bottom is called the denominator of the fraction. The key to understanding division of whole numbers is contained in the following statement. Division is equivalent to repeated subtraction. Suppose, for example, that we would like to divide the whole number 12 by the whole number 4. This is equivalent to asking the question, how many 4s can we subtract from 12? This can be visualized in a number line diagram such as the one in Figure 1.10. In Figure 1.10, note that if we subtract 3 4s from 12, the result is 0. In symbols, 12 minus 4 minus 4 minus 4 equals 0. Equivalently, we can also ask, how many groups of 4 are there in 12? And arrange our work as shown in Figure 1.11, where we can see that in an array of 12 objects, we can circle 3 groups of 4, i.e. 12 divided by 4 equals 3. In Figure 1.10 and 1.11, note that the division, repeated subtraction, leaves no remainder. This is not always the case. Example 2. Divide 7 by 3. Solution. In Figure 1.12, we see that we can subtract 2 3s from 7, leaving a remainder of 1. Alternatively, in an array of 7 objects, we can circle 2 groups of 3, leaving a remainder of 1. Dividing 7 by 3 leaves a remainder of 1. Both Figure 1.12 and Figure 1.13 show that there are 2 groups of 3 and 7, with 1 left over. We say 7 divided by 3 is 2, with a remainder of 1. Division is not commutative. When dividing whole numbers, the order matters. For example, 12 divided by 4 equals 3, but 4 divided by 12 is not even a whole number. Thus, if a and b are whole numbers, then a divided by b does not have to be the same as b divided by a. Division is also not associative. For example, if we divide 48 by 8 first, we get 6, and then 6 divided by 2 is 3. On the other hand, if we group 8 and 2, divide 8 by 2, we get 4, and 48 divided by 4 is 12, which is not the same thing as 3. Thus, if a, b, and c are whole numbers, grouping a and b does not have to be the same as grouping b and c in the expression a divided by b divided by c. Therefore, division is not associative. Division by 0 is undefined. Suppose that we are asked to divide 6 by 0. In Figure 1.14, we have an array of 6 objects. How many groups of 0 do you see? Now, to divide 6 by 0, we must answer the question, how many groups of 0 can we circle in Figure 1.14? The answer: this is a meaningless request. It makes absolutely no sense to ask how many groups of 0 can be circled in the array of 6 objects in figure 1.14. Division by zero. Division by zero is undefined. Each of the expressions is undefined. On the other hand, it makes sense to ask, what is 0 divided by 6? If we create an array of 0 objects, then ask how many groups of 6 we can circle, the answer is 0 groups of 6. That is, 0 divided by 6 is 0. Dividing larger whole numbers. We'll now provide a quick review of division of larger whole numbers using an algorithm that is commonly called long division. This is not meant to be a thorough discussion, but a cursory one. We are counting on the fact that our readers have encountered this algorithm in previous courses and are familiar with the process. Example 3. Simplify 575 divided by 23. Solution. We begin by estimating how many times 23 will divide into 57, guessing 1. We put the 1 in the quotient above the 7, multiplying 1 times 23. Place the answer underneath 57, then subtract. Because the remainder is larger than the divisor, our estimate is too small. We try again with an estimate of 2. That's the algorithm. Divide, multiply, then subtract. You may continue only when the remainder is smaller than the divisor. To continue, bring down the 5, estimate that 115 divided by 23 is 5, then multiply 5 times the divisor and subtract. Because the remainder is 0, 575 divided by 23 equals 25. Application. Counting rectangular arrays. Consider the rectangular array of stars in figure 1.15. To count the number of stars in the array, we could use brute force, counting each star in the array one at a time, for a total of 20 stars. However, as we have 4 rows of 5 stars each, it is much faster to multiply 4 times 5 equals 20 stars. Application area. In figure 1.16a, picture 1 inch squared. A square with 1 inch on each side. In figure 1.16b, pictured as 1 foot squared, a square with 1 foot on each side. Both of these squares are measures of area. Now, consider the rectangle shown in figure 1.17. The length of this rectangle is 4 inches and the width is 3 inches. To find the area of the figure, we can count the individual units of area that make up the area of the rectangle, 12 square inches, or 12 inches squared in all. However, as we did in counting the stars in the array in figure 1.15, it is much faster to note that we have 3 rows of 4 square inches. Hence, it is much faster to multiply the number of squares in each row by the number of squares in each column. 4 times 3 equals 12 square inches. The argument represented above leads to the following rule for finding the area of a rectangle. Area of a rectangle. Let L and W represent the length and width of the rectangle, respectively. To find the area of the rectangle, calculate the product of the length and width. That is, if A represents the area of the rectangle, then the area of the rectangle is given by the formula A equals L times W. Example 4. A rectangle has width 5 feet and length 12 feet. Find the area of the rectangle. Solution. Substitute L equals 12 feet and W equals 5 feet into the area formula. Then the area formula is A equals L times W, so we get 12 times 5, and 12 times 5 is 60. Hence, the area of the rectangle is 60 square feet.